Good day, ladies and gentlemen. Today we are talking a little bit about the diffraction of waves. Now, the diffraction of waves is a little bit different from a previous video that you might have seen, where we spoke about diffraction of a single light ray moving to a perspex or a glass block or something like that. What we are talking about here is more the wave front. And obviously a wave front is very different from a single ray of light. I apologize if you can hear the dog barking. She's been more crazy than usual this morning. Now, the first, I suppose, principle of diffraction is that you need to understand diffraction refers to the bending. In our previous video that you might have seen, we had the bending of a ray of light. Now we have the bending of a wave front. Now a wave front, they are usually represented in textbooks as a bunch of lines like that. Now what that basically means is that either you have a wave that is just moving in a straight line, like ripples in water perhaps, and these are either the crests or the troughs, or if you are trying to look at particles moving, then each of these would be a particle or something along that line. But we're talking about wave fronts. If you want a more detailed video on wave fronts specifically, you can request that. However, it is not at all necessary for what we're talking about today. I just wanted to make the point that a single wave is different from a wave front. Now, the classic example is a usually water wave and a little obstruction. So we have a solid object and we have some waves coming in. Now, very obviously, if this is water, let's say for purposes of the example, they are not going to be moving through this solid object. So they are going to stop. Okay, nothing is going to be happening on this side. And on this side over here, they are going to continue on all happy as if nothing's really happened. But as soon as they get to this point, that's when something strange starts happening. Now I'm just going to draw a few of them like that. What pretty much happens is that this end of the wave sort of gets dragged, it gets slowed down. If you want to continue the example of water, the individual water particles that make up that wave, that make up that movement, are experiencing increased friction because of this object, and as such, because the particles are being dragged, they are moving slower. So this end of the wave is moving slower than this end of the wave. So the wave front actually bends. So what we have is we have the wave front sort of doing this. The other classic example is when you have two objects. And you have your waves coming in. Now, the same thing, very obviously, they are not going to go through the solid object. But right here in the middle, they can go through. And we have exactly the same thing happening, except now, rather than one side versus the other, it is the middle versus both sides. So while the middle will continue to move at full speed, the sides are going to get dragged and slowed down, and the wave front will bend. So what we're going to have is we are going to have little bends starting over there. And eventually the wavefront is going to be a semicircle rather than a straight line. And this actually creates some fairly interesting phenomenon. Now this of course happens with both light and sound and all kinds of interesting things, but one of the easiest examples is of course water. Now a practical example, perhaps, if you're at the beach and you are, let's say the beach is over here and the waves are coming in like this, and there's a big chunk of rock. So the waves are coming in and they are crashing against the beach over there. Right here there's going to be no waves, but because of the drag the waves are going to bend a little bit. So you will still have waves breaking on the beach a little bit in to this protected area by the rock. If you live next to a beach, I advise you to perhaps have a look next time you go to the beach if you can see something like this. It's a very nice, practical, real world way to actually see it. Now, this of course happens with light as well. Now, this is something that I can't really illustrate to you, but pretty much what happens is, and this is something you can do at home, it's an experiment you can do. If you have an object and you hold the object and you shine a light from behind the object, technically you should not be getting any of that light. I mean, if I take my little flashlight over here and I shine that from behind my hand, none of the light should be reaching my eyes. But if I take something that is just the right size, I don't think my finger is the right size. No, it is not. What you will notice is that the light does sort of bend. Now you can do this, the easiest way to do this is with a screw. So what more or less happens is, if you look at it from the top, you've got the screw and you've got your light source. So the light rays are coming in and they are hitting the screw. The light rays are not going to move through the screw. Light cannot move through a solid object as dense as a screw. The light right here, on the other hand, it's going to get diffracted. It's going to sort of bend. So the wave front is going to do something sort of like this. So if you're looking at the screw from the front, then this little bit on the side, right here, is going to be illuminated. The bit in the middle is not. Now I regret vehemently that I do not have something that is the right size. I don't know if you can see it if I do this with my pen, but you can sort of see that there's a little bit of light right along the edge of the black bit, but not in the actual middle. This is an experiment best done in a darkened room, but it is actually an experiment that you can do at home. The practical applications of this, in my opinion, are not that important for you right now. It's more important that you actually know what diffraction is and how it works. Now, we can actually do some calculations, because of course we can. Now, what we can calculate is the degree of diffraction. And if we go back to our example where we had two objects and the wave front moving in, then we can say the degree of diffraction, say degree of diffraction, is proportional to the wavelength of these waves and wavefronts divided by W, where W is the width of this aperture. So you can calculate how much the waves actually will bend. You can do something very similar with sound waves as well. Sound waves can also be diffracted, and I think this is perhaps the easiest way to illustrate diffraction. If you were to say have a hallway in your house and your room is at the end of the hallway and there's another room over there. If you were to say be over here and you were to talk to your brother or your sister or whoever who is over there, the sound waves of your voice is moving like that, but your brother can still hear you because right over here they are bending and they end up, if you actually go far enough, to sort of be traveling in a straight line again. So wavefronts can bend, and we can calculate the wavelength of the sounds we hear using an equation, and that is going to be V is equal to frequency lambda. The speed of sound in air is equal to, let me just write that, speed of sound is equal to 343 meters per second. And the lowest frequency that the human ear can hear is 20 hertz. So if we fiddle with our formula a little bit, we get lambda is equal to velocity over frequency. That is, of course, 343 over 20 for our example's sake. And that means that the wavelength right here that we are getting is 17 meters. Now, this is not something that is truly useful to calculate, in my opinion, because for me, from a practical perspective, what function does this serve for a grade 11 student anyway? Now, of course, there is the argument to be made that you need to be able to think and do the calculations and all of that, which is why I am doing the little example. But as I said, the most important thing for me is that there is an understanding of diffraction and how it works, because you're not going to be able to do any calculation if you don't actually understand diffraction. Now, I realize that this video was a little bit haphazard with little drawings and explanations and calculations all over the place. If you want me to make a dedicated video specifically about the calculations involved in diffraction, this aperture, the degree of diffraction, tell me so. If you want me to make a separate video going into depth on the actual diffraction of waves and some practical, not applications, but practical examples of them, tell me so. But this is just a sort of introduction. So if you have any issues, you are welcome to ask questions via the comments, or like I said, if you want a more dedicated topic specific video. Until next time, ladies and gentlemen, have a good day.